Today's notes are brought to you by Circles. Our notes are 12-1 and the title is Tangent Lines. Go ahead and set up about half of the page for vocabulary and one theorem, and we'll be doing 3 examples at the bottom. And as a note, you will need a marker for these notes. So let's start first at the very top with some important vocabulary. The 2 words we're going to be talking about today are tangent and point of tangency. And I want you to note that tangent and tangency, they both have some kind of similarities there. They're related to one another. So I'm going to go ahead and start by drawing a tangent line, okay? And I'm going to move it through. Now, right now, if I put the line right there, that is not a tangent line, because the definition is that a tangent line can only cross a circle at exactly one point. That could be a tangent line. Let's try another one. This could not be a tangent line. Not yet, not yet, not yet, not yet. Right to the edge. That could be a tangent line. Okay, and a tangent line can also go right up to the edge too. It can only touch right there. But you have to know in your mind that if this line were to continue, it would actually only touch once. Okay? So that is a tangent. So the definition of a tangent line, we're going to go ahead and write that in, is it's a line. Actually, let me move tangent down here. Tangent is a line that crosses a circle at exactly one point. So the red line would be a tangent line. Okay, the next thing that we're going to talk about is the point of tangency, and that kind of makes sense. The point of tangency is exactly the point, the one point, where the line, the tangent line, crosses the circle. So I'm going to call this the point where the tangent line crosses the circle. Okay, now we're going to actually learn about what a tangent and point of tangency do with a circle in the next theorem. Okay, so now we're going to finish the top half of our notes, and we're going to copy this theorem. The theorem says, if a line is tangent to a circle, this is the hypothesis, and I want you to leave a little space here, then the line is perpendicular to the radius at the point of tangency. And this is the conclusion. So let's see what that looks like. So if you have a line that's tangent to a circle, so here's that same circle we drew, and now let's draw that tangent line. Let's see if I can draw it only touching it once. Pretty great job. Okay, so I'm going to call this, there's my circle. So it says if you have a circle, and I'm going to call this circle O. So here we go. If AB, so I'm going to name this line A, B is tangent to circle O, then, well, what will happen? Okay, so I'm going to grab my circle, and with a little bit of magic, I'm going to bring that circle in. So if AB is tangent to this circle, well, then what happens? Okay, so it says that the radius, so I'm going to draw the radius in, that connects to the point of tangency. So this is the point of tangency. If I connect that to the center, those are 2 points, that's my radius, then what? Then the tangent line is perpendicular to the radius. That means I can say that those hit at a 90-degree angle, and that's this theorem. Now that we know about the relationship between tangent lines and circles, let's see if we can try a problem. So here's what I'd like you to do before we even start the problem. You're going to need to copy down the directions and this diagram, and then unpause the video when you're ready. Here's what it says. Segment ML and segment MN are tangent to circle O. So these are 2 tangent lines. What is the value of x? Okay, go ahead and pause the video, and when you're ready, unpause it, and we'll start the problem. The first thing I noticed is that they said they were tangent to the circle. That means that that line is going to create a 90-degree angle at the point of tangency. That would mean that right here at that point of tangency and right here at the point of tangency, I'd be looking at 2 90-degree angles. Now they asked me to find x, and x happens to be an angle. Alright, so now I know I'm looking for an angle, and it happens to be inside of this shape that has 4 sides. So now I'm going to wonder, what do the angles in a quadrilateral add up to? Now, this is way back in chapter 5. Do you remember this? The angles in a quadrilateral add up to, are you thinking 360 degrees? You're right. Okay, so let's go ahead and do our calculations here. I've got one angle that's 117 degrees. I have a 90-degree angle. I have another 90-degree angle. And I have, oh, I forgot one. I forgot my x. And I have my x degree angle. So I've got 1, 2, 3, 4 angles, and they should add up to 360 degrees. So I'm going to go ahead and combine 117 and 90 and 90, and I will spare you the calculations. If you add those 3 numbers together, you're going to get 297 degrees plus x degrees is 360 degrees. Now, if you wanted to find out what x was, you just subtract that amount from both sides, and I would find that x is actually 63 degrees. For example 2, the question is segment ML tangent to circle N at L? Is this segment right here tangent to this circle? If it were tangent, then this angle right here would be 90 degrees. So how can we test to see if it is? Well, what I didn't draw in the picture is that N and M were actually connected, and this measurement was actually 25 inches. Now, if that's given, then I can really check to see if this is really 90 degrees by using the Pythagorean theorem. So let's check. 7 squared plus 24 squared. Does it equal 25 squared? Okay, I know 7 squared is 49, but we're going to have to do these calculations to see if it really is equal to 25. Okay, 4 times 4 is 16. 4 times 2 is 8, plus 1 is 9. Here's my placeholder. 2 times 4 is 8, and 2 times 2 is 4. And there we go, 576. And I know 25 squared is 625. So now the question is 576 plus 49 equal to 625? That's 15, 11, 12, 6. It turns out that they are equal. And since they are equal, that means that it must be a right triangle, so my answer would be yes. Okay, and for your last example, it asks, what is the radius of circle C? So you're going to draw your blue circle with the center C. There are 2 lines here, and even though it doesn't say it, BA is tangent to circle C. So since I know that it's tangent, I can say that this is a right angle. And they're asking me to find the radius. So the radius is here. And it's also right here, from this point to this point. So what we're going to actually do here is we're going to look at this triangle. I'm going to draw it outside of the circle so we can really see the measurements. So here's the radius. This is 12. And what is this whole length? It's not r, it's not 8, it's r plus 8. So now I'm just looking at a right triangle, and I can use the Pythagorean theorem. This leg squared plus this leg squared should equal the hypotenuse squared. So that's r squared plus 12 squared equals r plus 8 squared. Now I know already you're looking at this thinking, gosh, I don't remember how to do this, but remember, r plus 8 squared is the same thing as r plus 8 times r plus 8. And if you FOIL that, that's first, outside, inside, last. You get r times r is r squared. R times 8 is 8r. 8 times r is 8r. and 8 times 8 is 64. That means you're really looking at r squared plus 16r plus 64. So back to our equation, I have r squared plus 144 equals r squared plus 16r plus 64. Now my goal is to find r, or the radius. So I'm going to start by seeing if I can isolate some stuff. I'm going to subtract r squared from both sides. And when I do that, I end up getting 144 equals 16r plus 64, because there's exactly one r squared on both, so it becomes 0. Now I'm going to subtract 64 from both sides. I get 16r equals, I'm going to need some more space here. 16r equals, let's do this calculation. 144 minus 64, well, that's 0. And 14 minus 6 is 8. So that's 80. I'm going to divide by 16 on both sides. And I have to ask myself this question: how many times does 16 fit into 80? I'm going to guess 5. 5 times 6 is 30. 5 times 1 is 5 plus 3 is 80. That's a good guess. So my radius is 5 yards.